Dear 4th grade students at the Department of Economics, this is our 4th recorded lecture for the econometrics module. The current presentation mainly discusses functional forms of regression models. The main source of the current presentation is Chapter 6 of Gujarati 2004. The current presentation covers three functional forms. These functional forms are the double log model, the growth models, and the reciprocal models. The log linear model is also known as the double log model and the constant elasticity model. In this model, the regressant as well as the regressors are all in logarithmic form. Consider the model expressed in equation 6.5.1. This model is known as the exponential regression model. By taking the natural logarithm of the regressant and the regressor, this model may be expressed as shown by equation 6.5.2. In the last model, if we rewrite ln beta 1 as alpha, this model is linear in the parameters alpha and beta 2. In addition, it is linear in the logarithm of the variables y and x, and thus this model could be estimated using the OLS method. Because of this linearity, these models are termed as log-log or double log or log linear models, as I mentioned earlier. If the assumptions of the classical linear regression model are fulfilled, then the parameters of equation 6.5.3, which is shown below, could be estimated by the OLS method. An attractive feature of the log model, which has made it popular in applied research, is that this log coefficient measures the elasticity of y with respect to x. Hence, if y represented the quantity of a product demanded and x its unit price, the slope coefficient measures the price elasticity of demand. If the relationship between quantity demanded and the price is as shown in figure 6.3a, the double log transformation as shown in figure 6.3b will then give the estimate of the price elasticity. Note that according to this model, the elasticity coefficient between y and x remains constant throughout. This explains why this model is called the constant elasticity model. Look at figure 6.3b. It shows that the change in ln y per unit change in ln x, that is to say the elasticity, remains the same no matter at which ln x we measure the elasticity. It is worth mentioning that although alpha hat and beta 2 hat are unbiased estimates of alpha and beta 2, beta 1, that is the parameter entering the original model, when estimated as beta 1 hat, as the anti-log of alpha hat, is itself a biased estimator. However, in most practical problems, the intercept term is of secondary importance, and thus there is no need to worry about obtaining its unbiased estimate. In the two-variable regression, the simplest way to decide whether the log linear model fits the data points is to plot the scattergram of ln y against ln x and realize if the scatter points lie approximately on a straight line, as shown in figure 6.3b. Now, let's consider a numerical example for the double log model using data provided in table 6.3 in your textbook. This table gives data on 4 variables. Of interest to us for the current example is the total personal consumption expenditure and expenditure on durable goods. Both are measured in 1992 billions of dollars. Assume that we wish to find the elasticity of expenditure on durable goods with respect to total personal consumption expenditure. If we plot the log of expenditure on durable goods against the log of total personal consumption expenditure, we will see that the relationship between these two variables is linear. Therefore, the double log model is likely to be appropriate. The regression results are shown here. From these results, we could say that the elasticity of expenditure on durable goods with respect to total personal consumption expenditure is about 1.9. This indicates that if the total personal expenditure rises by 1% on average, the expenditure of durable goods increases by around 1.9%. Hence, expenditure on durable goods is very responsive to changes in personal consumption expenditure. In other words, we could say that it's elastic. It is elastic. This is one reason why producers of durable goods keep a keen eye on changes in personal income and personal consumption expenditure. Recall from the mathematical economics course you studied in the previous semester the well-known Cobb-Douglas production function. This function could be estimated using the ordinary least squares method through taking the natural logarithm of all variables. In this double log regression, B2 is the partial elasticity of output with respect to the labor input, holding all other variables constant. In other words, B2 gives the percentage change in output for a percentage change in the labor input holding all other inputs constant. Similarly, B3 gives the partial elasticity of output with respect to the capital input holding all other inputs constant. Another interesting property of the Cobb-Douglas function is that the sum of the partial slope coefficients B2 and B3 gives the information about returns to scale. If this sum is 1, then there are constant returns to scale. That is, doubling the inputs will double the output, tripling the inputs will triple the output, and so on. If this sum is less than 1, then there are decreasing returns to scale. That is, doubling the inputs results in increasing the output by less than double. Finally, if this sum is greater than 1, there are increasing returns to scale. That is, doubling the inputs leads to an increase in the output by more than double. An issue of great interest to economists, the government, the business sector, and policymakers is the rate of growth of key economic variables. These key economic variables include GDP, money supply, population, employment, and interest rates. The semi-log models are used to find out the rate of growth of these economic variables. In such models, either the regressand or the regressors are in the log form. In addition to the semi-log models, researchers sometimes estimate linear trend models. Let's start with the linear trend model that is expressed by equation 6.6.9. In this regression model, we regress y on time, where y is the dependent variable under consideration. Note that the time variable t is known as the trend variable. If the slope coefficient in this regression is positive, there is an upward trend in y. In contrast, if it is negative, there is a downward trend in y. To illustrate the growth model shown by equation 6.6.9, let's consider the data on expenditure on services given in table 6.3. The regression results are shown below. Based upon these results, we could say that over the period starting from the first quarter of the year 1993 to third quarter of the year 1998, on average expenditure on services increased at the absolute rate of about $20 billion per quarter. In other words, there was an upward trend in the expenditure on services. Now we will consider the log linear model to find out the growth rate of personal consumption expenditure on services over the period starting from the first quarter of 1993 to the third quarter of 1998. That is the dataset of table 6.3 we have just considered. Recall that the formula expressed by equation 6.6.1 represented the well-known compound interest formula. This formula has been studied in the course of Mathematics of Investment and Finance. Equation 6.6.1 can be transformed into a linear model by taking natural logs of both sides, as shown by equations 6.6.2 and equation 6.6.5. We add the error term to equation 6.6.5 to take into account the possibility that the relationship may not hold exactly. The regression equation in 6.6.6 is like any other linear regression model in that the intercept and slope parameters are linear. The only difference is that the regressant is the logarithm of y and the regressor is time. Models like 6.6.6 are called semi-log models because only one variable, in this case the regressant, appears in the logarithmic form. Such a model in which the regressant is in logarithmic is termed a log-line model. In this model, the slope coefficient shown by equation 6.6.7 measures the constant relative change in y for a given absolute change in the value of the regressor, that is time in our case. In practice, we multiply the slope coefficient by 100 to compute the growth rate. Note that the outcome of 100 multiplying the slope coefficient is also known as the semi-elasticity of the regressant with respect to the regressor. Equation 6.6.8 shows the regression results of estimating the growth rate of expenditure on services using the log linear model shown in equation 6.6.6. According to the equation 6.6.8, the expenditure on services increased at a quarterly rate of 0.743% over the period under consideration. The compound rate of growth is computed by taking the antilog of the estimated slope coefficient and subtracting 1 from it, then multiplying the difference by 100. Thus, the compound rate of growth rate on expenditure on services with about 0.746% per quarter, which is slightly higher than the instantaneous growth rate. Of course, this is due to compounding effect. Now, suppose that we want to find the absolute change in y for a percentage change in x. A model expressed in equation 6.6.11 would be very helpful in this regard. The model shown in 6.6.11 is a semi-log model. It is termed as a len-log model. In this model, the regressor is logarithmic, but the regression is linear. Thus, what does the slope coefficient tell us in this model? The slope coefficient measures the absolute rate of a change in the regression for a given percent, a change in the value of the regressor, as shown by equation 6.6.12. This equation could be rewritten as shown in equation 6.6.13. This last equation states that the absolute change in y is equal to the slope coefficient times the relative change in x. Thus, if the relative change in x it changes by say 1%, then the absolute change in y is obtained by multiplying the slope coefficient by 1%. Therefore, when regression 6.6.11 is estimated using the OLS method, remember to multiply the value of the estimated slope coefficient by 1% or to divide it by 100. If you don't keep this in your mind, your interpretation in an application will be highly misleading. The len-log model is used in Engel expenditure functions. According to Engel, the total expenditure that is devoted to food tends to increase in arithmetic progression as total expenditure increases in geometric proportion. In other words, the share of expenditure in food declines as total expenditure increases. Let's revisit example 3.2 in food expenditure in India. That is, we have previously discussed. As a first approximation, we employed the OLS method to estimate a model that is linear in variables, both the regressor and the regressant. Remember that we have plotted these data points in our last interactive lecture. This figure is shown here. This figure indicates that food expenditure increases more slowly as total expenditure increases, giving credence to Engel's law. So our task now is to re-estimate the relationship between food expenditure and total expenditure using the len-log model. And let us see the results. The results of fitting the len-log model to the food expenditure data of the 55 Indian households are shown here in the current slide. According to these results, the slope coefficient is around 257. What does this slope coefficient tell us? Remember that here we are interested in finding out the absolute change in y for a percentage change in x. In other words, we are interested in computing the absolute change in the total expenditure in food in terms of rupees due to a percentage change in the total expenditure, say by 1%. So if the total expenditure increases by say 1% on average, this leads to about 2.57 rupees increase in the expenditure in food of these 55 families included in our sample. The reciprocal model represented by equation 6.7.1 is nonlinear in the variable x, but it is linear in the regression parameters beta 1 and beta 2, and thus it is a linear regression model that could be estimated using the OLS method. From the mathematical economics course, we know that as the independent variable x increases indefinitely, the second term of equation 6.7.1 approaches 0, and thus y approaches the limiting value of the intercept, that is beta 1. Given that this model is nonlinear in x, the slope of this model is not constant. This slope is given by the following equation. In other words, we could say that the slope depends on the value of the x at which we measure the slope. According to the slope equation, if beta 2 is positive, the slope is negative throughout. In contrast, if beta 2 is negative, the slope is positive throughout. One of the most important applications of this model is the Phillips curve that you studied in macroeconomics. Let's consider the data given in table 6.4 in your textbook. This table provides cross-sectional data for 64 countries on child mortality and other variables such as per capita GNP. We are interested in examining the relationship between the child mortality and per capita GNP. The data points of these two variables are plotted in figure 6.7 that is shown here in the current slide. From this figure, it is clear that as per capita GNP increases, the child mortality decreases. This is expected, of course, because people can afford to spend more on health care, assuming that all other factors remaining constant. But according to this figure, the relationship is not a straight line. This is because, as we see, as per capita GNP increases, initially there is a dramatic drop in child mortality, but the drop gradually becomes less as per capita GNP continues to increase. Thus, let's fit the reciprocal model of 6.7.1 to this dataset. Results of fitting the reciprocal model to quantify the relationship between the child mortality and per capita GNP are shown in the current slide. As per capita GNP increases indefinitely, child mortality approaches its limit value of about 82 deaths per thousand. This is the value of the beta 1. And as mentioned earlier, the positive value of beta 2 implies that the rate of change of child mortality with respect to per capita GNP is negative. So there is a negative relationship between the two variables as mentioned earlier. Table 6.6 summarizes the main functional forms of two variable regression models discussed in the current presentation. For each model, the table provides the slope coefficient and the elasticity. Choosing the functional form is a practical issue. However, the theory itself may inform us about the appropriate functional form, as we have mentioned many times when studying the polynomial models. Functional forms discussed in the current presentation are the double log model, which is also known as the constant elasticity model, the growth models that include the linear trend model and the semi-log regression models, and the reciprocal models. In the double log model, both the regressand and regressor are expressed in logarithmic form. The regression coefficient attached to the log of a regressor is interpreted as the elasticity of the regressand with respect to the regressor. It is suitable to use this model when modeling the demand function and the production function of Cobb-Douglas. In the semi-log models, either the regressand or the regressor are in the log form. In the semi-log model, where the regressant is logarithmic and the regressor x is time, the estimated slope coefficient multiplied by 100 measures the rate of growth of the regressant. These models are often used to measure the growth rate of many economic variables, such as employment, population, GDP, money supply, and so on. In the semi-log model, if the regressor is logarithmic, its coefficient measures the absolute rate of change in the regressant for a given percent change in the value of the regressor. Finally, we studied the reciprocal models, in which the regressor is expressed in inverse form to capture the nonlinear relationship between economic variables, such as the relationship between the per capita GNP and the child mortality, the example we studied, and such as the well-known Phillips curve you studied in macroeconomics. Now we have reached to the end of our lecture. Thank you so much.